types of computers. It runs on Windows, Macs, and Linux. If you're on Windows, you can, through the Start menu, call it up, and you should be able to find an AnyLogic 7 Professional installed there that you can call up. So, Raheem, maybe you could get extra, if there's any TAs out there, we're going to be needing their services. Okay. I believe it was installed with Professional. Priyasri, could you confirm that? Oh, it's University? Okay, then we'll use the University one. That's so University will serve us for all of our needs in the week. You may see me occasionally demo a more advanced feature. Okay. So when you come up to AnyLogic, you should see a screen like this, which shows a variety of resources. Do people see that? Okay. So once this is up, I'd like you to go up, and as we'll exercise later in the week, go up to the Help menu and do example models. Okay. You can also get to it through this link here, but this is a more general way that we'll be using throughout the week and is always available. So if you do Help example models, you should be presented with a screen such as this here. And I'd like you to go click on the How-To models that's on the left-hand side. So this left-hand side menu originally looked like this, and there's a thing that says How-To models, maybe barely visible there. You may have to scroll down to it in some of your cases to see it. But How-To models, if you go click on it, you should see all these models made available here on the right-hand side. And I'd like you to go into this model called SIR agent-based here. Okay. And see if you can open that up. Okay. I'm going to re-rehearse that again, just so you can see the full scope of what I just did. So I did Help example models. I then clicked on How-To models here on the left-hand side, and then I scrolled down and I went to SIR agent-based. Okay. There we go. Okay. Okay. Who needs TA help following along? TA help? Okay. So anyone else? No? Okay. So we're going to, we've just loaded in our first AnyLogic model. Over here on the left-hand side in this projects area, we see information on the structure of this model, which right now remains likely mysterious to a lot of people, but we're going to be looking at it in more detail. So here, we're going to be exploring that structure a little bit, and in the course of the week, we'll be learning more about what it means. So let's double-click on person here, and you should see an area that we call the canvas open up here on the right-hand side. So what we see here, so agent-based models capture, they capture operationally a theory as to how the world works or how it could work. Sometimes it's a counterfactual theory that we investigate to understand its logical implications. Sometimes it characterizes an abstraction of the world we think is probably pretty accurate, and we're interested in understanding its correspondence with real-world phenomena. So if you double-click on person, what we see here is kind of a representation of what it means to be a person, personhood, personness, with respect to this model. So here we see that there's a set of information related to a person, and it's in a structured form. We call this form a state chart, hence its name up at the top. And the state chart depicts information about the state of a person at a given point in time, here being divided between a susceptible state, an infectious state, and a recovered state. And then there's a set of these black lines, which represent transitions between states. So these represent processes by which an individual might go from being susceptible to infectious through a process of infection due to contact between two people. or by which someone may recover. Now, I think in your model, this is something which came from a previous exercise. I think in your model, you're going to see that. There should be no return transition there. We're going to be adding that over time. So here we see a depiction of an individual over time, and at a given time, they're divided into one of these three states, and they're in exactly one state. The states are mutually exclusive and collectively exhaustive, and over time, they progress between those states. So this is kind of the theory associated with an individual, and one of the pieces of that theory that we're going to be highlighting in just a minute is that there's contact. While they're in an infectious state, there's some contact which is going to take place between them and other individuals, by which other individuals can get infected. And we're going to be taking a look at the implications of that here in just a minute. So this is a depiction of individuals. And now let's go up to main here. And by double-clicking on the main so-called class, which is kind of the stage in which the agents strut, it's the context in which the agents are embedded. It's kind of a depiction of the broader world in which the agents circulate. We can call it in different ways. In this context, it depicts a space on which agents will be interacting. Each agent is going to be located at one situated location in this space. And at any one time, there's going to be a count of the number of individuals in different states reported up here at the top. Now, if you scroll over here to the left, you'll actually see that there's a little bit more than meets the eye initially. So here we have a population indicated here with this depiction people, and there's some parameters associated with this model, some encoding of our assumptions that we want to make about this model involving what size the population should be, the average illness duration, the contact rate, and the infection probability given contact. So here we have a set of parameters that can run with the model. So, ladies and gentlemen, I'm going to just clean up this model, which has been a little bit affected by a previous boot camp here, and I'd like you to ask yourselves, given that we have people situated in space, given that they are in a broader population, which is going to be spread over this rectangular area, and given that they contact other individuals, in this case, individuals in the cardinal directions, north, south, east, and west, that is left, right, up, and down, how would you expect, what might you expect in terms of the behavior of this model? What might you expect to see when we run this model? Anyone? If we start one person infected, what would be the implications? Okay, there should be a propagation of infection between people. And I hear the word outwards, meaning that it's not merely a propagation which will appear at random places within this space, but it will be spreading out in some way. And let's go try testing our intuitions against what actually results from, at a very precise level, the consistent implications of what we've seen here. So we're going to go over to simulation, and if you click on simulation, you'll notice that it imposes certain assumptions on the model. It gives an average illness duration, a contact rate, an infection probability, and a total population infection probability here given contact of 50%. It's a highly transmissible illness and a total population. And I'd like to run it. So you right-click on that and do run. The project provides several different ways of running models. You could right-click on it and click run. Another way that you can run it is through model run or through this button up here. I'd like to suggest for the balance of the boot camp that people do it so by right-clicking, because it allows you to be very specific and visual about specifically which experiment you want to run. Which experiment do you want to conduct now? So I've just run that. I did it again by right-clicking here and doing run. And a window will pop up, which is allowing us to kick off the simulation. Before this model kicks off, I'd like to suggest that people click on this button down here in the lower left, which says Customize Toolbar, Customize Status Bar, and I'd like to suggest that you select the Model Time component of this.
The binders are here and the faces have been done.
Okay, thanks. Yeah, yeah. No, we'll do that in a bit. Okay, so here again, you do Model Time here, and you'll select Model Time with the checkbox. Okay, it's through this little right-facing arrow here at the bottom. Okay, anyone need TA help? Okay, TA need over there. Okay, so having done that, I'd like now to press this button that says Run the Model here, and what you'll see is very similar to what was suggested earlier. Your name? Dayu. What Dayu suggested in terms of model behavior. So we see infection starting at a certain place and spreading outwards. So here we have susceptible people characterized as yellow. We have infectious people characterized as red, and we have with gray color denoting the recovered people within the population. Here we have a count of the number that fall into each category up here, shown at the top, and we see a spreading outwards of this infection, just as Dale mentioned. Okay, so within this context, can anyone explain, can anyone give some intuition for why we see this pattern that's before us on the screen? What is it that's going on? Why is it all yellow outside, and why is it all gray on the inside and then red only on this periphery, on this tinge? Anyone? Question?
You're propagating away from that. It can only pass through once, so you've got this interface between the uninfected and the infected.
Good.
Because there's no feedback, you become infected again. It leaves behind the recovery.
Good. Good. Okay. So people start in the susceptible state. We seed an initial infective. That infective can only infect neighbors in the north, south, east, and west. So it starts propagating out in a localized fashion, which grows over time, and that wavefront that's growing over time is successfully expanding because the previous generation's new infectives are now infecting new people next to them. We see it spreading out. We also see some raggedness on the periphery. Anyone want to advance some theory as to where that raggedness may be coming from? Why isn't this a perfectly regular shape here? Yeah, there's some randomness. So what we'll find is if we go to this theory of a person, as it were, we have transitions here which are not deterministic in nature. They're not pre-specified exactly what they'll be doing at a given time. Rather, they're stochastic. They're uncertain. So we have a certain rate of recoveries, and we have a mean time someone stays infectious. Some people recover before that. For some people, it takes longer. And moreover, there's differences in who happens to get exposed. In this exposure component here, we're sending messages to random neighbors. Sometimes a neighbor may be the first one to get, so sometimes people may infect the person on the north-south side first. Sometimes an infective individual may infect the person on their west side first. And based on the vagaries of those stochastics, you'll see little differences in how the infection is spreading over time. Okay, ladies and gentlemen, I'd like to further ask you to customize your screen by going up here to the Customize toolbar and going down to the Model Navigation area. And in the Model Navigation area, you'll find the ability to go down to the level of a single person. So scrolling down here, and I'll do this again. What I did is I went and you started with a situation like this. By clicking here, you can choose Model Navigation, and you should be able to drill down to the level of particular people within the population. Here, for example, is a person who's recovered. Here's a person who remains susceptible. And by scrolling through these people, you can understand the state of different individuals in the population. In other words, this broader space that we see here is composed of a broad set of individuals, and we have recourse to information at the level of an individual on their current state, and in fact, if we wish to impose a bit of structure on it, to their longitudinal state, their trajectory over time. Okay? Okay, ladies and gentlemen, having highlighted this, who needs TA help? Yeah.
What is time?
Okay, so it's a good question. So we'll go talk more about that in the course of the week. But here, if we go up to the model as a whole, you'll find that there's a time unit specified for the model, which is given here as days. And AnyLogic actually maintains a calendar that can be used to actually relate, you know, the choice of time units to an actual calendar in terms of years and months and days, takes into account leap years and all those sorts of things. In this particular model, it's somewhat more stylized. We're saying that the yardstick for time is days, and we're going to be expressing these parameters that are given, these assumptions about the model as specified by an experiment in terms of days. So, for example, the average illness duration here will be 15. In other words, on average, it will take 15 days for someone to recover from an infectious state to a recovered state. Days we imposed on the model as our time unit. You can choose a wide variety of other time units. Is that helpful? Okay. Okay. Yes, Dylan.
Just so everyone knows, can you show them how to get to that date thing? Because it's also one of those obscure parts to get to the model.
Sure. So if you go click on the model as a whole, and you look here in properties, you'll see days described here. So one of the things that it'll be very important, one of the skills will be very important to build up in the course of this week is to know where to look for certain types of information within your models. One of the biggest challenges with AnyLogic in particular as a platform is there's lots of information squirreled away at different places. Later in the week, we'll be highlighting something that will give you the ability to document all pieces of that model within a single place. You can do it up on the menus here by exporting model documentation associated with the model, and that will show it all in one place. But otherwise, you will often be browsing around a model to find different types of information, and you want to develop a sense as to where to look. For example, do I look in person? Do I look in main? Do I look as the model as a whole? In this case, the time unit is something that's specified for the entire model. We're imposing a time unit of days that's going to be consistent throughout the model. So wherever we use a bit of model time, it will be expressed in days. So if we use 10 at a place, it will be expressed to mean 10 days. If we use 0.3, it will be 0.3 days. And that will afford us a chance to have a consistent interpretation across the entire model, and therefore it's specified as a model as a whole as compared to on a per experiment basis. Okay. Any other questions? Okay, so let's continue running this model, and I'd like you to take note of how long it takes for this expanding periphery to reach the edge here of the screen. So we're running it, this indicates we're running it flat out as fast as possible. And you'll see it's approaching the edge here, and I'm going to say it's just about time 300 that it hits the edge of that screen, okay? Just about time 300. Okay, so we've just run this model with a set of default assumptions encoded by the structure of the model to be sure, but also associated with this experiment. I'd like now to see how we can modify this model. Much of this week will be spent building up models, and this will be your first chance in changing model assumptions. So to get you to do this, I'd like you to go add in a new experiment, okay? And the easiest way to do this in this case will be to to copy this experiment. So right-click on it and do copy. Alternatively, you can do edit, copy. And then up here, click on the model as a whole and do paste. Okay? So let me do that again. So I right-click here on copy, and we're going to do paste up here at the top. Okay? And we're going to create a set of experiments initially which run this model under different assumptions concerning the specifics of the natural history of infection, how long it takes people to recover, how long it takes them to eventually to lose immunity. So I'd like to create three additional experiments where we make different assumptions about the model, so we can run those and see the implications dynamically. So in the first such experiment, I'd like to call it very, very brief infection. So how do we do this? So clicking on this, if we go down to name, you can say very brief infection, and you do so in the name area. You'll notice that I'm typing this all as one word. It's quite particular about these things, and in this case, you will want to use it all in a single word, and if you want to put what looks like spaces, you can put underbars between them. My own preference is to put capitals at the beginning of each word, using a convention known as camel case. Capital V, capital B, capital I, you could kind of read it out, what the distinct words in it from the capitalization. This will be a consistent need throughout the boot camp, is to give names to things in the model with a single word. It's a constraint imposed by the underlying platform. Okay? So this will be a very brief infection. I'd like to make the average illness duration here 5. So what did I just do? I copied and pasted this, and then I went to, I named it, very brief infection, and then I went to this average illness duration. I changed it to be 5. Okay? Who needs TA help? TA, stand ready for deployment. Okay. Deployment to Sector 5. Okay. So, any questions on this? If people are comfortable with this, I'd like to go through that same process with actually 3 additional scenarios. So I'd like you to do one scenario with 10 days, another scenario with 15 days, another scenario, excuse me, the medium is already done. That's the default. And then long 50 days. So let's add 2 more. One for a brief infection. We'll go through the same process. We can copy and then right-click here and paste. Okay. And this will be called brief infection, not very brief, but brief infection. And I'd like this to be a duration of 10 days. Okay. So the shortest one was 5. This one is going to be 10. And then we're going to do one more. So we can copy that in the same way and do paste here. And we're going to add a final type of experiment, a final scenario that where we can alter the assumption. This will be called long duration infection, okay? Or prolonged infection. How about that? That's better. Prolonged infection. Prolonged infection, and this will be 50 days, 50. Okay? So what are we doing here? We are successively adding in different scenarios that will allow us to investigate the implications of a theory of how the world works with different detailed assumptions about the duration of time people stay infected. This model is capturing a theory as to sort of how the world might work, and it allows us to understand the implications of that theory in terms of things we might care about, which might be, for example, how quickly the infection spreads, or the total number of people that get infected, etc. Okay, so ladies and gentlemen, what have I done overall here? Through copy and paste, copy here, paste up here, I have created 3 additional scenarios. One of them with a very brief infection with a average illness duration of 5, another with a brief infection, average illness duration of 10, another with a prolonged infection, average illness duration of 50. Who needs TA help? TA? TAs? There's a free machine up here, I think. A free machine over on this side, I think? Oh, okay, I can't. Thanks, yeah. Okay, okay, we'll, you might want to speak with Merlin if, there he is. The magician appears. Great. Okay, so who needs TA help for this? Okay, I'd like now to try to work to understand the implications of these altered assumptions. We had an original scenario that we had run earlier with an infection duration of 15. How will it impact it if we have a very brief infection? Does anyone want to volunteer? How do you think that this might impact things? To have a very brief infection. How would it visually change things? Yeah. Okay, so it might propagate more slowly, and visually, would we still see an expanding ring of sorts with gray inside and yellow on the outside?
Not as thick.
Not as thick. Okay, it might die out. I hear. Okay, so a variety of different theories about how it might evolve. Let's run it and see the implications. At least in a single run. Merlin, do you need to? Okay. Let's make a single run here. Okay, we actually just started it, and what happened? It says it's finished. If we go look at the time, it'll say something that might surprise us. The time is infinity. Anyone have a theory about what happened? Yeah, it recovered before we had time. Now let's run that again. I mean, is that consistent every time? Well, once again, we get the same results. Now, if we ran it enough times here, we'd find that on sometimes it might actually take off a little bit, but then die out. So here we're in a situation where the infection is so brief, we don't see any outbreak at all. That initial person. There's a plug over here, Annie? There, yeah. So the initial infection will die out without imposing burden on the balance of the population. That index infective recovers so quickly they don't infect even on average one person. But if we ran that enough, we would find there are some cases where it takes off and some it takes off a little bit, and some where it just dies out completely. And that's due to the vagaries of chance. Let's run brief infection now. How do we expect this? Well, again, it's briefer, so a lot of the descriptions previously still obtain. So we might expect a smaller, thinner periphery. And I just turned on model time. I did that through this sort of golden triangle pointing to the right, and we see that it spread out. If appearances don't fool us, it's actually spreading a bit quicker. There's actually less work for the package to do. I'm going to just time this here. Anyone want to wager? Will it reach the boundary more quickly or less quickly? Same. Okay. So here we go, and if anything, it's very brief. It may be within the realm of sort of not significantly different than. It's just that particular time it was just over 300, and we could keep on running it and test, but it's very, very close in time. Now, why is that? So people are infected for less long. Wouldn't that mean that they're infecting fewer people, and therefore the infection should infect fewer people overall, and should perhaps as well propagate less quickly? Why is it that we're not seeing that here? Well, we're still getting the entire population infected. People are still maxing out the number of people they can infect north, south, east, and west. And they're doing that within a shorter period than 10 time units. And so, while this is a briefer infection, they still infect all their neighbors with almost certainty. And the infection will therefore go on to that next generation just as quickly as it did before. So we see a situation where it's pretty similar to what we saw with the default case. Now, how about a very prolonged infection? A situation where the infection is assumed to keep people infectious for 50 days. Who would like to advance some theory as to how that will be different? Well, how will it look different?
A lot more red.
A lot more red. It'd be a lot thicker of a periphery, of a boundary around it. Okay.
And when you talk about
Yeah.
duration, are you talking about the duration of symptoms or duration of the person's
Contagiousness. Now, it is possible, and there may be some example models, I have to think about this, which will distinguish between incubation period and latent period, and which will distinguish between the occurrence of symptoms on the one hand versus infectiousness on the other. And that's readily representable. Because we're dealing here with so simple a model for our first learning, that's not, here we're dealing purely with the issue of infectiousness or transmissibility of the infection. Is that helpful? Okay. Okay. So here we're running the infection out, and you'll notice it's taking a lot more time. There's actually a lot more going on. People are staying infectious for longer. They're contacting their neighbors on an ongoing basis, but those contacts fall on stony ground. They don't infect anyone because the people around them are by and large already infected or recovered. So there's a lot more going on, and as a result, it actually takes longer calendar time to actually accumulate it. It reaches the end just about the exact same time. But we have these, you'll notice there are these lingering infectives in the middle here. These people who remain infected for a very long time because of the longer duration of infection. Okay, ladies and gentlemen, so we've just seen... Yeah, question. Yes.
So contrasting the default and the very brief infection,
sure,
where it's able to get off the ground.
Yeah.
Is there a principled way, so we've sort of bounded between failures, so that nonlinearity?
That's right.
Is there a method or way of thinking about how to get closer to figure out where that nonlinearity occurs, or how do I?
It's a great question, and
apart from just putting in different times.
Indeed. So there's a wide variety of types of models people use to investigate situations like this. Some of them lend themselves to analytic investigation in the form of formally and as we say in closed form, being able to write formulas to capture the location, say, of a tipping point through analysis of the model. And there's a broad class of models based on ordinary differential equations, which are very amenable to that. And broadly, those correspond to a type of modeling known as system dynamics that we're going to be talking about in the course of the week. With agent-based modeling, typically you are required to perform your exploration through repeated runs of the model. And there are several reasons for that, but at the most fundamental level, we lack a formal mechanism, a formal analysis methodology, which can allow us to identify the so-called stability of a model such as this. So a model like this can examine unstable behavior. You drop someone into a population, it affects the population, it changes the state radically versus you drop them in and it disappears. It's a matter of what we call, at a mathematical sense, stability of the system, and we lack a good way of analyzing it for these models. And so the typical way of analyzing these models is actually to make successive runs of the model. Now, as we'll be talking about later in the week, this typically involves running the model many, many times to develop confidence as to the statistical variability with a given set of assumptions. But for a typical model, we don't have a really nice way of sort of analytically identifying the shape of that curve other than empirically exploring it through successive runs. Is that helpful? And that's part of the trade-off between modeling methods. It's an important trade-off. Very good question. Okay, I'd like to reflect on a little bit of what we've seen here. So when we ran all but the briefest scenario here, we saw a somewhat similar picture in that we saw this this expanding periphery, and we saw individuals who were different colors, sort of arranged in almost segregated areas here, with yellow outside, red in the periphery, and then gray on the inside. And we gave some understanding about where that was coming from. But can anyone tell me? I mean, this pattern that we see here so repeatedly for so many experiments, where is that in the model? Where is it that it says, you know, there's going to be an expanding ring? Where is it that it says that, you know, red is going to be inside the ring and yellow on the outside, and red in the sort of band around that? Is that anywhere in the model? I mean, do you see it anywhere poking around here? If you poke around, is it visible? Well, the answer is no. There's no place that says assume that there's going to be an expanding ring. No place does it assume that the number of infectives is going to rise over time, sort of stabilize, and then decline as there are fewer and fewer people to infect, eventually reaching zero. Nowhere is that expressed in anywhere in the model. Instead, it's what we call an emergent property of this model. That results from the model. That's an implication of the model, that pattern that we see, but it's not pre-programmed into the model. It's not forced upon the model. It's not in any way directly hardwired into the model that we're going to have a pattern like that. That pattern is a result of the interaction of a wide variety of different assumptions, some of them concerning how long people stay infected, some concerning how infection is transmitted, that it's transmitted at a certain frequency of contacts, and that it's transmitted to nearby people in space. It's related to the fact that people are in a bounded space, this kind of rectangular space. All of those combine to yield the sort of behavior that we've seen visually. That behavior is something that may be surprising at times. We weren't quite sure what to expect from the very brief infection, whether it would yield a persistent infection, an infection that stuck or not. And sometimes models like this can lead to quite big surprises in terms of the actual behaviors. The point is that the behavior of the model was not something we wrote into it. It's not like writing a regression equation where we pre-specify the form that links up the independent variables and the dependent variable. We pre-specify it to be a Poisson regression, or pre-specify it to be a logistic regression. Instead, here we're getting a behavior over time that's emerging from the interaction of a wide variety of different pieces of this model. And it's one of the most salient and important aspects of this system. Another aspect was noted earlier, which is nonlinearity here. We can change these parameter values, and for certain ranges of those parameters, we may see pretty consistent behavior, and then for some, the behavior has changed totally. We saw a tipping point, a value of parameters where the infection no longer caught hold, and others where it spread in a quite consistent fashion. So we can see nonlinear behavior here. And nonlinearity is a term that has many implications, including important implications for reasoning about interventions. Yeah. Thanks. Okay, so I'd like now to make a more radical modification to this model. So, yes, question?
Just a side note, when we were watching your model run, it was very much faster.
Oh, okay.
So the model memory, is there a drawback to studying it as it's on your?
So that's a good question. One of the reasons I chose to make those changes in the way I did is because I actually chose that particular strategy to make it a little bit more fast because I didn't want to go into the plumbing. But if anyone had a really slow model and maybe pursued those things a different way, I would note that this particular model, because of the vagaries of how it's constructed, if you go into the experiment, there's this thing that says maximal available memory, and that makes a really big difference for how quickly it runs. And on certain machines, you may really want to make it larger. Some may need less memory, and so that can have a significant material impact on the speed with which the actual experiment is running. Okay, and this is one of the reasons I did copy paste rather than asking you to create a new experiment from the get-go. Okay, other questions? Great question. So what we've been modifying here is we've been tweaking around the edges of this model. We've been modifying the assumptions about how long people stay infected. Ladies and gentlemen, let's change the structure of the model. We have a model structure that's characterized by these pieces we see before us. Here we have this natural history of depiction, a natural history of infection depicted here. We have this space in which people are embedded. Let's go see where that space is described. If you go up to main, double click on main, scroll down in these properties for main here, you'll see that there's a space. People are arranged in a certain neighborhood, which gives them four neighbors. Actually, this gives them eight neighbors here in space. So those all contribute to the structure of the model. When broadly in modeling, we say that structure determines behavior. That behavior we saw came out of interaction of components within a certain structure of the model. The theory of the model drives the behavior. So ladies and gentlemen, let's change the theory of the model. Let's add a reflection of waning immunity into this model. How would we do that? How do we add a situation where immunity is waning over time? Anyone? Okay, if we were to think about waning of immunity, loss of immunity, how might that be described in a model like this? We have these transitions and we have these states. Let's suppose we want to stay within the bounds of these same states. How would we describe a situation where someone loses immunity? Where's an immune state right now captured? Recovered. Okay, so how would we capture loss of immunity? Yeah. Okay, recovered to susceptible. Okay, so ladies and gentlemen, let's modify the theory of how the world works in more than a simple matter of degree by changing our understanding of how people can progress in their natural history of infection. So ladies and gentlemen, to do this, I think you're going to be in a situation where you have over here on the left-hand side a projects and a palette window. Do you see that? Can anyone indicate? Yeah? So I'd like you to click on palette here, and you're going to see a set of choices here. You'll probably see these choices up front. And down here, there'll be something that says state chart. This palette is going to be your persistent friend throughout the course of the boot camp, and perhaps for the course of your life. So over here on the palette side, you'll see a set of choices as to different pieces of logic, pieces of mechanism that you're going to be able to build into your model. And I'd like you to go down and select the one that shows this sort of little yellow thing and a black thing before that. If you hover over it with your mouse, it'll actually say state chart. Okay? Do you see that? Who needs help here? Okay, TA's deployed to sector 1. Okay. Okay, other TA help needed? Okay, so let's add in a transition, and let's watch carefully as I do this. I'm going to drag in a transition from recovered to susceptible. Now, I could do this in a number of ways. My preferred way to do it is to drag it in so that its originating end goes to recovered here. And you'll notice it turns green there, meaning that it's connecting. So I'd like to suggest you do that. Okay. So how do I do that? Let me do it again. I drag in here, okay, like that. And then I'd like you to go up here and drag the other end to susceptible. Okay? So let me rehearse that again. I drag in a transition here. It should connect as indicated via the green on its from end, and its arrow end will go up to susceptible. Now, currently this transition actually describes a movement from recovered to susceptible, but for some it will be an aesthetic affront because it crosses the state in the middle. And I agree that it's ripe for misunderstanding. So I'd like to reroute it. Ladies and gentlemen, you can click on this, double click on that transition and drag it out. And you could create something instead like this. So I'm somewhat aesthetically handicapped myself, but to me this looks more natural. Sure. So I'm going to rehearse the whole thing here. So I'm going to drag in a transition like this, and it turns green on its from end. I'm going to drag this end up here, and then I'm going to double click somewhere along the transition. That's not to double click in the state, just because it will get misunderstood as clicking on the state. And then you could drag it like that. It's this little handle that you could use to drag. Okay. Questions? Okay. Okay, folks. So I'd like to now go to this transition and look at its properties. The properties of this transition. We're going to give it a name called waning immunity. Okay, waning immunity. And you'll notice that we have additional choices here. I'd like to set it says triggered by timeout right now, and I'd like to keep it as a timeout transition. In other words, it'll occur a certain number of days after someone is infected. I'd like you to set the timeout to be 150 days, 150 days, okay? So here we have individuals that either due to mutation of the underlying pathogen, such as mutation of the outer membrane protein, it will evolve over time, and therefore it will evade the immune response of an individual. It could be due to waning of immunity due to change in underlying immunological complement over a longer period. Here we're describing this 150 days, so it's more likely to be a shorter-term process, perhaps due to very rapid mutation. So this will be a timeout of 150 days, 150, associated with this transition. We're looking at the properties of this transition, okay? A very helpful skill to develop in any logic is to be able to take a look what is selected at the current point, either in the canvas or over here in a projects window, before you make sense of the properties. It's important to know what am I looking at, and to keep that in mind when you're adding things to the model, particularly. So here we're selecting this transition here. The properties are showing we're setting the timeout to be 150 days. Okay, so ladies and gentlemen, we've set the timeout, or set it so that people will lose immunity after 150 days. How do you expect that to affect the dynamics that we've seen? How would you expect it to affect the behavior of the model? Anyone?
You get secondary waves because after
Good.
a period of time, those behind can interact and start propagating again.
Good. Okay, so let's test our intuitions with this. Excellent. So go to projects, and let's first simulate our default sort of baseline case. where we had that average illness duration of 15. This is the very first case we ran. And if we right-click on it, again, we do right-click here and do run, here we'll see something very similar to what we saw earlier, but there's no change. Why is it we don't see a change yet? It hasn't passed 150 days. Okay, now we're in the zone where 150 days. What do we see? Okay, this is a new generation of susceptibles. From whence did those new susceptibles come? Yeah, they came from the recovered individuals before. They recovered after a certain period of time. So you see this propagating fringe of the number of susceptibles over time as people lose immunity from the previous generation. And yet you see a new outbreak occurring in here within the area, of yellow. Why is it we see this outbreak? Can anyone give some understanding? Why is it we see these recurrent sort of patterns of red emerging? Why is it we see these recurrent sets of new infectives? Say that again? So what is it that infects these people, these new susceptibles whose immunity has waned and they've become again susceptible? What is it that has infected them? Yeah, one of the infective individuals from the previous generation, right? From that previous sort of wave. Okay, so here we see these kind of recurrent waves of infection, just as Ron prognosticated, and each new generation is beset by infection that was triggered from the previous generation. Okay, so now let's run these other assumptions. How about we do it for a prolonged infection? What do you think we'd see here? Anyone? How would it be different? Anyone? Okay. So what are we seeing in here that might make a very material difference in what happens when we see waning immunity? Waning immunity is approaching.
You're going to have more infected left behind to break out fast.
Beautiful, beautiful. So here we have more infectives left behind. And so here we have susceptibles coming in, and they're almost immediately getting infected here. So the waves of infection are less pronounced in this case, right? We get the less distinctive kind of successive waves associated with them. Okay, so here we have a lot more infectives overall, and the waves are less distinct. Okay, ladies and gentlemen, let's continue our exploration with the other scenarios. Each scenario varying the detailed assumptions about to impose as far as duration of infection, but each scenario adhering to this general theory about how things work, that people lose immunity. So let's run the brief infection. Here we have an infection that's briefer. It lasts less long. Okay, so here we're running out. How might that affect things?
Because there's not enough infected bodies around to really reinfect everybody else.
Yeah, so here you'd actually see it says it's finished. If you went and looked at the time, it would say infinity. It knows there's no more work to be done. The task is over here. It's done. There's nobody who could possibly get infected. Everyone's susceptible, and that's it. Because there were no leftovers. There were none of these kind of residual people from that previous generation of infection to infect that next generation. The next generation has been spared. The next generation, due to fast recovery, if the previous one has been spared the ravages of the infection that it would otherwise beset it. Yes?
That's a good point. This model takes into is operated on the assumption that only the people from the previous generation of the previous outbreak
Yeah.
can infect new generation.
That's right.
Of course, in real life, so people coming from other areas.
Right. That's very important point.
That's the one point. And the second is, of course, so we have the immunization.
Yeah.
That actually plays an important role in the distribution of
Right. 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 That's right. Good. So I like what I'm hearing, and those are some very good points. If time afforded it, we could actually simulate the effects of having people arriving over time who are occasionally infectious. And here there's a very crude representation, as you say. It's dichotomous representation of immunity. You're either fully immune or not at all. And it's only induced by actual infection of an individual rather than by other means. And one of the big virtues of these sorts of models is the fact that they can capture actually time-varying immunity on the part of an individual and immunity of different strengths. And it turns out, for reasons on which I published, but which are not obvious up front, while a dichotomous division is quite typical in a lot of the modeling literature, in particular the modeling literature undertaken with compartmental system dynamics, ODE, they all are referring to pretty much similar types of models here. While it typically assumes a dichotomous distinction, you're either susceptible or you're immune with a certain level, maybe a different one for vaccine-induced as opposed to naturally induced immunity. One of the big insights is that you can actually get very different results from a model like that compared to a model where you actually simulate continuously decreasing immunity over time on the part of an individual. So in other words, an individual doesn't simply go from recovered to susceptible. Instead, they decay gradually in their strength of immune response. And you could capture it with these sorts of models. And there are models I'll be showing later in this boot camp on Wednesday, likely, which where we'll see exactly that phenomena. And we'll see people's immunity, immune dynamics, build up of immunity, immune memory over time that decays, and where later exposure will have a very different impact depending on the strength of their residual immunity. Yes.
Sorry,
yeah.
I interrupt. I was just wondering if you or anybody's ever modeled those Titus media outbreaks again, because it took me an awful lot to convince my physicians that I'd had it and I needed to be revaccinated.
Huh.
Because they didn't believe
that it waned.
It decayed over time.
Huh.
And of course, in Alberta, they had that several years ago. That adult outbreak.
Interesting. Well, Dr. Doroshenko here could probably comment on that offline, because being from Alberta and with the province of infectious diseases in our neighboring province. So yeah, I'm not aware of otitis media models. There may be some that I just have overlooked, but that would be an interesting thing to look at, certainly. Yeah. So good, George? Yeah.
Maybe a more mechanical question. How does it know when to stop?
Oh, great. Right. Yeah. Yeah, so it's a great question, George. And because I don't want to stand between you and the food that lies outside, I'll answer it briefly. The basic deal is that each experiment you can set the stopping related factor, so you can decide whether you want it to run for a fixed amount of time or on an ongoing basis. In this case, it's set to stop never. You can also set it to stop at specified time here, and in this case, it so-called never stops, but it knows that there's no work to be done after a certain point where there's all susceptibles. Then it knows that in this case, there's no other things that are going to happen, that can happen, that are going to trigger a change in the current state. It knows there's no set of events that lead to people to be introduced that are infective into the population. It knows that there's no possibility that there's going to be a change somewhere else that's going to trigger a new infection. So it just knows, okay, that's all the work that has to be done, and it's safe to assume that from now on it's going to be in an unchanging state. You can set it so that instead it runs at till a specified time, in which case then you have a very defined time for each run, say the time 200 days or 1,000 days or what have you. You can also impose that context. And if memory serves me, and I'd have to double check this, but I could certainly demonstrate it if that's the case. You can also set it so under a certain condition the model will stop, a condition of your choosing, and that's also sometimes useful. If there's no more than 10 residual infectives, stop the model. Is that helpful? Okay. There's one other hand up. Yes. Okay. Maybe we'll pursue it offline. Okay. So there's snacks, food, and it's time for a washroom break. And maybe we could come back in about 5 minutes and resume. Again, the washrooms are down to the left, all the way at the end of the hall, and then you'll find them on the right-hand side.